Hello everyone. In this lecture we will discuss about the diffusion of component A through non-diffusing component B with the help of example. So in this lecture we will discuss the flux of component A, the flux of component B, the velocity of component A and the velocity of component B with the help of example. So the problem is ammonia, which is component A, which is diffusing through non-diffusing component B. The component A is ammonia while the component B is air. The stagnant layer of air is 1 centimeter thick. So this is a stagnant layer of air which is 1 centimeter thick. This is the air component B, while this is ammonia, which is component A, and it is diffusing through this non-diffusing component air. The 1 centimeter thick layer at 25 is present at 25 degrees centigrade and 1 atmospheric total pressure. So the total pressure here in this place is 1 atmosphere. In this place 1 atmospheric pressure, and the temperature is 25 degrees centigrade in this place. The partial pressure of ammonia on both sides. So the partial pressure of ammonia on both sides of the stagnant layer of air is the partial pressure of ammonia on both sides of the stagnant layer of air is PA0 0.9 atmospheric pressure and PAL is 0.1 atmospheric pressure. PA0 is 0.9 atmospheric pressure while PAL is 0.1 atmospheric pressure. So PA0 is this. The partial pressure of ammonia in this place is 0.9 atmospheric pressure while partial pressure of ammonia at this place, which is distance L, RZ is equal to L. The partial pressure of ammonia at this place is 0.1 atmospheric pressure. So the partial pressure of ammonia in this place is very high. This is total ammonia and this is some air molecule in this place. So the partial pressure of ammonia will definitely decrease as we go from lower position to higher position in the stagnant layer of air. So air is non-diffusing component B. Remember, air is non-diffusing component B, while ammonia is diffusing component A. So the given data is diffusion of component A through non-diffusing component B, and the diffusivity of ammonia in the air is 0.214 centimeter square per second at 25 degrees centigrade and 1 atmospheric pressure. The diffusivity of ammonia in air is this one. This is given to us in the question. Now required, what is the molar flux of ammonia? What is the velocity of ammonia and air with respect to stationary observer? And C, the molar and mass average velocity of ammonia and air. The molar flux of ammonia with respect to observer moving with the mass average velocity. So first of all we will calculate the mass average velocity, and then we will calculate the molar flux of ammonia with respect to the observer which moving with mass average velocity, which is moving with some mass average velocity. So and and the part number E, what is the partial pressure of ammonia and what is the partial pressure of air along the diffusion path. So this is the diffusion path. The diffusion path is this one. Suppose this is the diffusion path. This is air molecule. This is the air molecule, and this is the ammonia molecule. These are the ammonia molecule. So ammonia molecule is diffusing through air molecule, and this from this position to this position, this is the diffusion path, which can be Z. This position Z is equal to 0, and at this position Z is equal to L. So at Z is equal to L, the partial pressure of ammonia will be PAL, and it will be equal to 0.1 atmospheric pressure. But when Z is equal to 0, the partial pressure of ammonia at this place will be PA0, and it will be equal to 0.9 atmospheric pressure. So and then we will calculate that what will be the partial pressure of ammonia in this stagnant layer of air, which is 1 centimeter thick and which is present at 25 degrees centigrade and 1 atmospheric total pressure. So solution, the molar flux of ammonia is this one. This equation is obtained from diffusion of component A through non-diffusing component B. This DAB is given to us, the diffusivity of ammonia and air is given to us. The P is total pressure, R is universal gas constant, T is the temperature 25 degrees centigrade, and L is the diffusion path. This is the L in natural log, P minus PAL, P minus PA naught. So remember, when diffusion of component A is through non-diffusing component B, so component B is non-diffusing, so the flux of component B will be 0. When A is diffusing through non-diffusing component B, then the molar flux of component B will be 0. In equation number 1, DAB is given, which is this one. PAL is 1 atmospheric pressure. PA naught is given to us, which is 0.9 PA naught. This PA naught is 0.9 atmospheric pressure. This PAL is 0.1 atmospheric pressure. L is the diffusion path. The length of diffusion path, which is 1 centimeter. So this is LRZ. This can be LRZ. You can put LRZ anything. So the length of diffusion path or the thickness of the stagnant layer of air is 1 centimeter. R is universal gas constant. Its value is 8.314 joule per mole into Kelvin. So Na is equal to, so putting value in this equation number 1. In this equation number 1, we will get Na is equal to this one. After some conversion, this is the universal gas constant, this is the temperature, and these are the conversion factor. So after putting value, we will get, this is the P minus PA, PAL, P minus PA naught. So the molar flux of ammonia through non-diffusing air at 25 degree and 1 atmospheric pressure is this one. 1.922 multiplied by 10 raised to power minus 5 mole per centimeter square into second is the molar flux of ammonia through non-diffusing air. So this is part 1. Now the part 2 is what is the velocity of ammonia with respect to stationary observer. So first of all, we will find the molar average velocity. So the formula for molar average velocity is U is equal to Ca, the concentration of ammonia multiplied by velocity of ammonia plus concentration of air multiplied by velocity of air divided by concentration of ammonia plus concentration of air. So there is no velocity of air because air is stagnant layer, so the velocity of air will be 0, this will be 0, this term will be equal to 0. So the molar average velocity will be equal to Ca UA divided by Ct. Now we know that UA velocity multiplied by concentration is nothing but flux, and we know the flux. We have already obtained this one in the part number 1 of this problem. So here we can put the value. This is the UCA and this is the so Ca and UA is nothing but the molar flux of ammonia. So we will put Na in place of Ca and multiply by UA, and this is the total concentration. So this is the Na value is given to us, this one, and this is the total concentration is nothing but from the universal gas law, C is equal to P by RT. So Ct will be equal to Pt divided by RT. So the total pressure is 1 atmospheric pressure, R value is given to us, and T is the temperature, which is 298 Kelvin. So after putting value, the molar average velocity will be equal to 0.47 centimeter per second. This is the molar average velocity of ammonia and air. So what is the velocity of ammonia at Z is equal to 0? At Z is equal to 0, the ammonia concentration will be very high. So we will find the velocity of ammonia at a place where the concentration of ammonia is very high. So but because at Z is equal to L, the velocity of ammonia will be very small. So we will find the velocity of ammonia at Z is equal to 0 position. So at Z is equal to 0, the partial pressure of ammonia will be 0.9 atmospheric pressure, which we have already obtained. So this is the molar average velocity. This is the concentration, this is the velocity, this is the total concentration. So this is the this one, this is equal to, this is the molar average velocity. Now the this UA can be obtained. This UA can be obtained from this equation. For example, I am writing it this UA will be equal to Ct multiplied by U divided by Ca. This is nothing but this will be equal to Ct multiplied by U divided by Ca. This is equal to UA. Now rearrange U divided by Ca divided by Ct. Ca divided by Ct is nothing but the mole fraction of ammonia, the total mole fraction, the mole fraction of ammonia. This is the mole fraction of ammonia. But so at Z is equal to 0 or L is equal to 0, where the concentration of ammonia is very high, Pa is equal to Pa0. So and Pa0 value is 0.9, which is given to us. So Ya is equal to Ya0 at Z is equal to 0 position. The Ya will be equal to Ya0. So this Y will be equal to Ya0, and this value is obtained, which is 0.47. Now Ya0 is equal to Pa0 divided by P, and this is P is the total pressure, which is 1 atmospheric pressure, and this is 0.9. So Ya0 is equal to 0.9 atmospheric pressure. So this value is obtained, which is 0.7, and this is 0.9. So 0.47 divided by 0.9, we will get the velocity of ammonia at Z is equal to 0 position. So this is Ya0 0.47. This is the molar average velocity, and this is the Ya0 value. So this is equal to 0.522 centimeter per second. This is the velocity of ammonia at Z is equal to 0 or L is equal to 0 position. Now the velocity of air is 0. So the velocity of air at Z is equal to 0 position will be also equal to 0, because air is not moving. We assume that air is not moving through ammonia molecule. So the flux of ammonia is also, the flux of air is also 0. So UB or velocity of air will be 0. Now what is the mass average velocity? The formula for mass average velocity is equal to U is equal to density of component A, velocity of component A, plus density of component B into velocity of component B, divided by density of component A plus density of component B. As we know that velocity of component B is 0, so this term will be equal to 0, and this is the density multiplied by velocity of component A divided by total density. Now remember, this is for two component system, ammonia and air. For multi-component system, you can add some other component to this formula. So now this is the density, velocity divided by total density. Now from ideal gas law, we know that P is equal to nRT, PV is equal to nRT, and we know that we can rearrange this equation, mole divided by volume. Now we know that mole is nothing but mass divided by molar mass. Mass divided by molar mass, this is the velocity, and we know that mass divided by volume is nothing but density, and this is the molar, the molecular mass of the mixture, which consists of ammonia and air. Now this is the universal gas constant. So rearrange this equation. This is the total density of the mixture is equal to the total pressure of the mixture, the total flux molar mass of the mixture. This is the universal gas constant, and this is the temperature, which is 25 degrees centigrade. Remember, this is the isobaric condition, so the temperature is constant, 25 degrees centigrade. So for component A, the density will be equal to partial pressure of component A, the molecular mass of component A divided by the universal gas constant, and temperature multiplied by temperature. So now we know that this is the mass average velocity, which is the partial pressure of component A into the molar mass of component A, and this is the velocity divided by RT. Now you can put this value. This is the density. Now the density value is this one, and multiply by velocity of component A, this one, and this is the total. This is the total density. So you can put this is the velocity. This is the velocity, and this is the velocity. This is the molecular mass. This is the partial pressure, and the total density is nothing but Pm divided by RT. So Pm divided by RT. RT cancel with RT, and this is the P divided by partial pressure of component A divided by total pressure, which is this one. This is molecular mass of component A. This is the molecular mass of the mixture. This is the velocity of component A. Now this is the velocity of component A. This is the Ya. This Ya is obtained from Pa divided by P, is nothing but Ya, mole fraction of component A. This is the molecular mass of component A. This is the molecular mass of the mixture. Molecular mass of the mixture is this obtained from this formula, A is the component A, which is ammonia. The molar mass of ammonia is 17 gram per mole per gram mole, and the molar mass of air is 29 gram per mole. So here you can put the molar mass of the mixture is the at z is equal to 0 position. The mole fraction of ammonia will be 0.9 atm, and the molar mass of ammonia plus the when the ammonia is 0.9, then we know that the mole fraction of air will be definitely 0.1, because Pa plus Pb is equal to P, and P is 1 atm. So this is the total, the molar mass of the mixture is 18.2 gram per gram mole. Now at z is equal to 0, or z is equal to 0, or L is equal to 0, phi is equal to P A naught, and P A naught value is this one, and UA is equal to UA naught. The UA naught value is already obtained, which is 0.522 centimeter per second. Now UA naught value is obtained 0.5. The YA value is also given at z is equal to 0 position. The MA value is also given, the molar mass of the ammonia, and this is the molar mass of the mixture, which is obtained 18. So this is the mass average velocity of the mixture, 0.439 centimeter per second. The mass average velocity of compound ammonia at z is equal to, or at L or z is equal to 0 position is this one, 0.439 centimeter per second. Now the molar flux of ammonia with respect to observer moving with mass average velocity. Now when observer is moving with this mass average velocity, or this mass average velocity, then the molar flux value will be this one, Z J A is equal to CA and to UA minus U. Now CA is nothing but, from the ideal gas law, this is nothing but PA divided by RT. Now the PA is at Z is equal to 0 position, PA is equal to 0.9, and this is the universal gas constant, this is the temperature, and this UA value is obtained already, 0.522 centimeter per second, and this is the mass average velocity U, which is this one, 0.43, this one, 439 centimeter per second. Now putting value, we will obtain the molar flux of ammonia with respect to observer moving with mass average velocity, this one. Now this is component A, this is component B, this is the temperature, pressure, we have already discussed this one. So the molar flux of ammonia with respect to observer moving with the mass average velocity, this one, will be equal to 3.05 multiplied by 10 raised to the power minus 6 mole per centimeter square into second. Now come to the part E. What will be the partial pressure of ammonia in the diffusion path, and what will be the partial pressure of air in the diffusion path? This is the Z is the diffusion path. So as we know that this is the molar flux of ammonia, this equation, P value is given, the DAB value is also given, PA0 and PAL, the PA0 value is also given to us, but PAZ or PAL value is a function of Z. So the PA, when Z is changing, the partial pressure of ammonia along the diffusion path will be also changes. This R and T value are also given to us. Now we have already obtained that the molar flux of ammonia along the diffusion path is this one, and this is obtained from this equation. This is the molar flux, and this is the DAB multiplied by total pressure divided by RTL, and this is ln P minus PA Z divided by P minus PA naught. So when we change Z, for example, the Z is the total distance is 1 centimeter. So when Z is equal to 0, the PA will be equal to PA naught. When Z is equal to 0.1 centimeter, the PA value will be equal to PA at 0.1 position. It will be changes. So now we know we will rearrange this equation. This value is given. We will multiply this to this side, the temperature. So this is the temperature, and this is the Z. So when we change Z, the partial pressure of ammonia will be changes along the diffusion path, and divided by this, and this is the total pressure. It will be equal to the ln P minus PAZ divided by this one. Now take E on both sides, so this cancel with this one, and this is E to the power this one, this term. So this is P minus PAZ divided by 0.1, and this E and this is constant, this multiplied by this divided by this is some constant. We will obtain some constant value, and this is the changing. Z is equal to changing, this is the variable. So when Z is equal to 0, phi is equal to PNR. So when Z is equal to 0, this term will be, the power will be 0, and this E to the power 0 will be equal to 1. So P minus P at Z will be equal to 0.1 at Z is equal to 0 position. So when Z is equal to 0, phi A will be equal to phi A naught, and phi A naught will be equal to 0.9, which we have already obtained. So when Z is equal to, now when Z is equal to 0.1, the PA will be equal to phi A naught, and phi A naught will be value will be some, we will obtain some value of phi A naught. Now how will we obtain the PB? So PA plus the partial pressure of ammonia plus partial pressure of air will be equal to 1, which is 1 atmospheric pressure. So PAB will be equal to 1 minus PA. So this is the graph along the, this is the diffusion path, 1 centimeter. When Z is equal to 0, the phi A is equal to phi A naught. So this is the phi A naught, which is 0.9 atmospheric pressure, and the PB will be equal to PB naught, which is equal to 0.1 atmospheric pressure. So now when we change value to 0.1 centimeter, the PA value will be decreases. So PA, the partial pressure of ammonia along the diffusion path will decreasing, and the partial pressure of air along the diffusion path will increasing. So we will obtain these curves along the diffusion path. So these are some curves which show us the partial pressure of ammonia and air along the diffusion path. Thank you very much for your attention. If you are new to the channel, please like and subscribe.